Okay, in this case here, what we have to do is to determine the convergence radius of these two series, two power series, and then calculate the sum. Actually, we're going to do both at the same time. So we're going to try to calculate the sums using using some procedure, right? And this procedure will automatically provide us what is the radius of convergence. Okay, so let's focus on the first one. Okay, the first one is this, right? The sum of n1 to infinity x to the n over n. Let's call this function f of x, right? Okay, we have to take into account where we are starting, right? And it's important where we start because we want the sum, okay? All right, so we have this function here. If we take the derivative of this function, what we get is the sum from 1 to infinity. Remember that you can take the derivative term by term. So the derivative of this is just the x to the n minus 1, right? It's n x to the n minus 1, the n cancels, so you just get x to the n minus 1. And if you shift the coefficient, the index, 1 unit up here, 1 unit down here, what you get is the sum from 0 to infinity of x to the n. Okay, we don't know yet what is the sum of the series that we want to calculate, but we do know what is the sum of the series that defines the derivative of the function we want to calculate, right? It's 1 over 1 minus x. This is the geometric series, right? And we also know the radius of convergence. So the radius of convergence of this one is going to be the same, okay? So the convergence of this one occurs in the same because the derivative and the function has both the same radius of convergence. Okay, if the derivative is equal to this, we need to calculate f as a primitive of this function. But the primitive of this function is, of course, minus the logarithm of 1 minus x. Okay? All right. Well, in principle, there should be an absolute value. The proper primitive should be an absolute value. But remember that the absolute value of x is smaller than 1. So this is never going to be negative. So we don't have to put an absolute value there. It's enough to put just 1 minus x. But there is also an arbitrary constant, okay? Because we can't determine this constant because for any constant this is a primitive, right? However, if this is to be this function here, and we evaluate this function at one point, for instance 0, okay? Since all the terms contain a 0 here, then the value of the function is equal to 0. So if we substitute here 0, right? F of 0 is equal to minus the logarithm of 1 plus c. This is 0, so this is equal to c. So c is equal to 0, and then we have the sum of our function. Okay, this is the sum of this function. So we have this minus the logarithm of 1 minus x is equal to the sum from 1 to infinity x to the n over n. Okay? This is, well, normally is easy to figure out when to apply this trick of the derivative. Normally is when you have power, you have the n in the denominator, and when you take a derivative, the exponent cancels with this denominator, right? Now let's go to the second series, this one here, and let me write it like this: the sum from 0 to infinity n plus 1 x half to the n, right? Because you have 2 to the minus n times x to the n. This is x half to the n, right? And just to avoid having annoying constants, we're going to introduce a variable t, which is just x half. Okay, so let's focus on this one. Here we have the opposite problem, right? Well, actually, it's easy to see that the derivative of this is equal to that, right? Well, it's easy to recognize here the derivative of this term here. So this is actually the derivative of this function, the sum from 0 to infinity of t to the n plus 1. All right? Now we can shift 1 unit down here and 1 unit up here. So we transform this into the sum from 0 to infinity, sorry, from 1 to infinity 1 to infinity t to the n, and we take the derivative. And since we are taking the derivative, it doesn't matter if we start at 1 or if we start at 0, okay? So we begin at 0, because starting at 0, we're just adding a constant, and when we take the derivative of a constant is equal to 0. So this can also be taken as this, because when we do this, we just realize that this is the derivative of this function here, okay? Now we automatically know, since the radius of convergence of this series is 1 for the absolute value of t, then we know that this series here converges when x half in absolute values is smaller than 1, which means the absolute value of x is smaller than 2. So 2 is the radius of convergence of this series here, right? Now let me continue, okay? So this one here is, the derivative is 1 over 1 minus t squared, okay? And if you remember from previous exercises, the sum of this series here, oh sorry, no, this is just, this is already the sum of this series. All we have to do is to replace t by x half, and then we have that. So if we replace t by x half, what we have is 1 over 1 minus x half squared, or if you just multiply here and simplify, what you get is 4 divided by 2 minus x squared. All right, so that is the sum of this series. The sum of this series is the sum of this n plus 1, well, 2 to the minus n, which is what we had before, right, times xn is equal to 4 over 2 minus x squared. And the convergence happens when the absolute value of x is smaller than 2.